Welcome to Square Ek Patshala. Today, we are analyzing the primary methods for combining capacitors in a circuit, series and parallel configurations. This split-screen diagram compares the two physical setups. On the left, in a series combination, the capacitors are connected end-to-end. Because there is only one path, the charge remains constant across every capacitor, while the potential drops across each component. On the right, the parallel setup features multiple branches. Here, the charge divides among the branches, but the potential remains identical across every branch. To derive the series formula, we begin with the variable that changes, the potential. The total voltage V is the sum of individual potential drops, V1, V2, and V3. By substituting the definition of potential, charge divided by capacitance, and factoring out the constant charge Q, we arrive at the inverse sum formula for equivalent series capacitance. In the parallel diagram, the charge is what divides. We start with total Q as the sum of Q1, Q2, and Q3. By substituting Q with C times V and acknowledging that the voltage V is the same for all capacitors, we can factor V out. This results in the direct addition formula, where equivalent capacitance is simply the sum of all capacitors in the parallel group. This comparison table highlights the physical consequences of these setups. Notice the net capacitance row. Series combinations result in a total value smaller than the smallest individual capacitor, while parallel combinations always increase the overall capacity of the system. Analyzing this mixed circuit, featuring 3, 6, and 4 microfarad capacitors, requires collapsing the network inward from the branches furthest from the battery. We focus first on C1 and C2. Because they share a single path without any junctions, they are a series pair. Take a moment to calculate the equivalent capacitance for this pair, then add that result to C3 to find the total capacitance of the entire circuit. The series combination of 3 and 6 microfarads yields an equivalent of 2 microfarads. This new block is parallel to the 4 microfarad branch, resulting in a net circuit capacitance of 6 microfarads. Applying the energy formula, 1/2 CV squared, gives us a total stored energy of 4.32 times 10 to the negative 4 joules. Determining this singular equivalent value is the necessary first step before solving for individual charges or energy values. Consider a series circuit with a 4 microfarad and a 12 microfarad capacitor on a 16-volt battery. Solving for individual potential differences usually involves a multi-stage process of finding total capacitance and total charge before arriving at individual voltages. The potential divider rule reaches these values in a single calculation. By multiplying the total voltage by the ratio of the opposite capacitor to the total sum, we find that the potential across C1 is 12 volts, which leaves 4 volts for C2. This method eliminates the need to calculate total charge as an intermediate step, which reduces the opportunity for arithmetic errors during a timed exam. Connecting a fully charged capacitor to an uncharged one causes a rapid redistribution of charge until their potentials equalize. During this process, the flow of charge creates heat and sparking in the connecting wires, resulting in a distinct loss of overall electrostatic energy. In this scenario, we connect a 600 picofarad capacitor at 200 volts to an identical uncharged one. The common potential is calculated by dividing the initial charge by the total capacitance of the new system, which settles at 100 volts. We calculate the energy loss using the delta U formula. To handle the picofarad units accurately, notice that the 10 to the negative 12 terms in the numerator and denominator cancel out. This simplifies the final result to exactly 6 microjoules. Subtracting the final total energy from the initial energy confirms this result. Because these two capacitors have equal values and one began with 0 charge, the system loses exactly half of its initial energy during the redistribution. When approaching these problems, always identify the combination types first, state your formulas before entering data, and remain diligent with prefix conversions. Following these steps ensures accuracy on your exams. Subscribe to Square Ek Patshala for further technical breakdowns. Practice these derivations, and we will see you in the next session.